Good morning. Today our goal is to interpret this velocity time graph and ultimately convert it into this position time graph. So let's commence operations. Before we get to this task, a brief review on position and velocity time graphs. Initially, I'm going to give the car a velocity of 4 meters per second. Let's see what that looks like. And so notice on our position time graph, it's a straight line. And the slope of that line is actually 4 meters per second. For a position time graph, the slope is the velocity. And here's what it looks like on a velocity time graph. Notice the slope of this line is exactly 0. That's because the object is not accelerating. And the acceleration here is 0. Now we're going to look at what acceleration looks like. Notice on a position time graph, acceleration is represented by a curve. Notice on a velocity time graph, constant acceleration is represented by a line. And the slope of that line is the acceleration. Finally, let's look at the case when the object, in this case the car, is slowing down. Again, on a position time graph, notice that when it's accelerating, a curve is used to represent the motion. On a velocity time graph, because the acceleration is constant, it's a straight line. And the slope of this straight line would be the acceleration, negative 2.5 meters per second per second. All right, so step 1, let's describe the graph. Well, we'll divide the graph up into 3 sections, A, B, and C. Section A runs from 0 to 4 seconds. Section B from 4 to 7 seconds. And section C from 7 to 10 seconds. So starting off with section A, from 0 to 4 seconds, it's constant velocity of 4 meters per second north. So how do we know it's constant velocity? Notice at time 0, the arrow is pointing at 4 meters per second north. 2 seconds later, it's still 4 meters per second north. And at 4 seconds, it's still 4 meters per second north. For section B, from 4 to 7 seconds, it's constant acceleration. In fact, it's slowing down, moving north. So how do we know it's slowing down and moving north? Looking at the arrow, at 4 seconds, it's 4 meters per second north. Sometime later, it's moving at 3 meters per second, still moving north. 2 meters per second, still moving north. 1 meter per second, still moving north. And finally, it comes to a stop. So just read the line very carefully. Clearly, the number is getting lower, so it's slowing down. In this case, the velocity, it's decreasing, it's slowing down. And it's always moving north, as the velocity is always positive. And finally, for section C, from 7 to 10 seconds, the object is stopped. How do we know that? Well, just look where the graph is at. It's always on the x-axis, which represents 0 meters per second, or stopped. All right, so now that we've described the graph, how do we take that velocity time graph and create this position time graph? Well, the key is to determine the area always between the x-axis and the actual line. That area represents the displacement. And so the area is drawn there for section A. Displacement is equal to length times width, as it's a rectangle. 4 seconds times 4 meters per second. And we end up with 16 meters. So what does this mean? It means that after 4 seconds, the car has moved 16 meters north. For all of these graphs, we always start off with our initial position at the origin, at 0. So at 4 seconds, the object is at 16 meters. Do we use a line or a curve to connect those 2 points? Well, we end up using a line. And so how do we know that? Going back to the velocity time graph, from 0 to 4 seconds, it's constant velocity. And constant velocity on a position time graph is a line. So what about section B? Once again, we calculate the area between the x-axis and the line, and that's the displacement. It's a triangle, so we use the formula half times base times height, or base times height divided by 2. The base is 3 seconds. Why 3 seconds? Because we're going from 4 seconds to 7 seconds. The height is 4 meters per second. Working through the math, we get 6 meters. So between 4 to 7 seconds, the car has moved an additional 6 meters. What does 6 meters mean? Well, if the car started out at 16 meters, then it ends up at 22 meters. Why 22 meters? 16 meters plus 6 meters. Why 7 seconds? Well, notice, when does section B end? Section B ends at 7 seconds. So now that we know how to locate our point, do we use a line or a curve to connect those 2 data points? Well, notice for section B, it experiences constant acceleration and it's slowing down. So recall that whenever we're accelerating, we need a curve. In fact, we need to choose a curve to represent the object slowing down. So here are your 2 options. Which one do you believe represents slowing down? Go ahead, think about this for a moment. This option represents slowing down. An easy way to think about this is the following. There always needs to be a smooth transition for the slope at 4 seconds. Now in this case, when we're moving from constant velocity to slowing down, that transition has to be smooth in terms of the slope. For this particular graph, as you can see, and this graph by the way is incorrect, the transition at 4 seconds is not smooth. We have a steep slope here going from a gentle slope. That's not a smooth transition. This graph represents a smooth transition at 4 seconds. Notice the slope of the yellow line and this line, it's more or less the same. What about section C? Section C starts at 7 seconds and ends at 10 seconds and the object is stopped. This is how we draw the line for section C. So now as an exercise, I'd like you to try to convert this velocity time graph into a position time graph. Remember, we always take the area between the x-axis and the line, and that area represents the displacement. Now I want to focus your attention on section D for a moment, because we didn't do an example like this previously. This is how we would draw the area for section D. Section D, the object is traveling south. How do we know that? Well, notice that the velocity at the end of section D, at the 10-second point, is -3 meters per second, meaning it travels south. Now, if you've already learned this formula, you can certainly use this formula instead of calculating the area. In fact, calculating the area and using this formula is the exact same thing. Let's use this formula for section A. V1 is the initial speed, or the initial velocity for section A. At 0 seconds, it's moving at 3 meters per second. V2 is also 3 meters per second. That's the final velocity for section A. And the time interval happens to also be 3 seconds. From 0 to 3 seconds, it's a total of 3 seconds has elapsed. Working through the math, it's 9 meters. And if you were to calculate the area, 3 times 3 is also 9. And so here is the final result. This is your final answer. I hope you try working through that graph to see if you could generate this graph. Ultimately, the best way to learn physics is through practice. And so, to summarize, today's lesson was on converting a velocity time graph into a position time graph. And to do that, you needed to calculate the area. The area represents the displacement. Hope you enjoyed today's lesson. Have a great day. Bye-bye.